distant corner of the cosmos, billions of light years from our world, a colossal star, 100 times heavier than our sun, approaches its dramatic end. In its final moments, it will erupt with a power surpassing that of 1,000,000,000,000 suns, sending ripples through the fabric of space-time. Tonight, we venture into a realm where the laws of nature strain under unimaginable forces. We'll witness eruptions brighter than galaxies, black holes that consume light itself, and the hidden interactions that hold the universe together. Prepare for a journey into a scale of power almost beyond human comprehension. Our exploration begins. Deep within every atom of your body, an unseen struggle unfolds. Protons crowded inside the nucleus should, by all logic, explode apart, their positive charges repelling violently, like two immense magnets pushed together. And yet they remain bound, restrained by the strongest force known to science. This force, the strong nuclear force, operates at a range smaller than a proton, yet its strength is absolute. It is measured to be 100 times stronger than electromagnetism, and 100 trillion times stronger than gravity. If gravity is a faint whisper, the strong force is a thunderous roar, capable of pulverizing mountains. This incredible force is carried by particles called gluons, which act like invisible chains, fastening quarks together to form protons and neutrons. The more you try to pull these quarks apart, the harder the force pulls back, like stretching a rubber band that grows thicker and more powerful the farther it is pulled. This strange property, known as confinement, ensures that a quark can never exist alone, no matter how much energy is applied. Inside every proton, 3 quarks swirl within a storm of pure energy, held in place by gluons that weave a web so complex that even supercomputers struggle to map it. If you attempt to separate quarks, the energy you inject doesn't free them. It creates new quarks and gluons, as though a chain you try to cut instantly sprouts new links. The strong force acts on distances so tiny that a femtometer, 1/4,000,000th of a meter, seems enormous by comparison. At such scales, the familiar rules of physics dissolve. Space and time themselves tremble with quantum uncertainty. This force determines what kinds of atoms can exist, how stars burn, and how matter behaves throughout the universe. Without it, protons would rip apart, atoms would never form, stars could not shine, and the universe would be little more than a cloud of hydrogen and electrons drifting through darkness. Yet, despite its strength, the strong force has one critical limitation. It reaches only as far as the boundary of an atomic nucleus, a distance so small that it defies imagination. Beyond that realm, other cosmic powers reign. Now step outward into the vast universe, where distance dictates destiny, and witness the result of gravity and light colliding in the most violent events ever observed. Somewhere deep in space, a beam of pure energy slices across the void at nearly the speed of light. In 10 seconds, it releases more energy than our sun will generate in its entire 10 billion year lifespan. This is a gamma-ray burst, the most extreme explosion nature can produce. Such events occur when the universe's most massive stars collapse into black holes. These giants, weighing 20 to 100 times more than our sun, burn through their fuel at a pace that would drain our sun dry in only a few million years. When their fusion finally ends, gravity overtakes them. Their cores collapse, launching jets of matter and radiation from their poles at nearly the speed of light. The implosion forms a newborn black hole encircled by a blazing disk of superheated gas. Twisted magnetic fields act like cosmic cannons, firing these jets with astonishing precision. They rip through the dying star and emerge as focused beams that hold their shape over unimaginable distances. Imagine a flashlight from Alpha Centauri glowing as brightly as a car headlight. That is the scale of this power. The light we receive today began its journey when the universe was young, carrying stories of the first generations of massive, violent stars. And yet, even this extraordinary power fades when compared with what waits in the darkness between galaxies. At the center of our own galaxy lies a monster 4 million times heavier than the Sun. Sagittarius A star consumes anything that approaches: clouds of gas, wandering stars, entire solar systems. Yet despite its terrifying mass, it is small beside the true giants of the cosmos. Some supermassive black holes weigh 40 billion suns and fit within a region smaller than our solar system. They warp space-time so intensely that nothing, not even light, can escape once it crosses the event horizon. Space bends and flows around them like water spiraling into a drain.
These titanic black holes didn't grow slowly. The most distant quasars radiate with unimaginable brightness, powered by black holes billions of times more massive than the Sun when the universe was less than 1 billion years old. How they grew so quickly remains one of astronomy's greatest puzzles. The leading theory proposes that they began as enormous seed black holes, formed from collapsing clouds of primordial gas. This gave them a vast head start, allowing them to gain mass rapidly through mergers and the consumption of nearby matter. As gas spirals toward a supermassive black hole, it heats to millions of degrees, forming a radiant accretion disk brighter than entire galaxies. Matter at the inner edge of the disk whips around at relativistic speeds, experiencing time so distorted that seconds for them would stretch into hours for an outside observer. Quasars, powered by these devouring giants, shine across the observable universe like cosmic lighthouses. Their light eclipses the combined glow of hundreds of billions of stars. Some black holes unleash jets of particles that shoot outward for hundreds of thousands of light years, reshaping galaxies, heating clouds, and shutting down star formation across entire regions. Still, even these cosmic titans are dwarfed by something far stranger and far more powerful. The surface of a neutron star is a frontier where the familiar rules of matter simply stop working. Here, physics behaves in ways that seem almost impossible. The magnetic fields are so powerful, they stretch atoms into long, needle-like strands, aligning them with the invisible lines of force. Under such extreme conditions, normal atomic structure cannot survive. Instead, matter transforms into bizarre states that exist nowhere else in the universe. Anything that falls onto a neutron star is crushed instantly into an ultra-thin layer only millimeters deep. The gravitational pull is so overwhelming that dropping something as light as a marshmallow from waist height would trigger an explosion comparable to a hydrogen bomb, releasing more energy than all the explosives used during World War II combined. Some neutron stars go even further. Known as magnetars, they possess magnetic fields 1,000 times stronger still, reaching the very limits of what the laws of physics permit. When their magnetic fields shift or fracture, the crust of the star can rupture in a violent starquake, unleashing more energy in a fraction of a second than the Sun emits in 100,000 years. These titanic magnetic eruptions can be detected across the Milky Way. The strongest magnetar flare ever recorded was so extreme that it briefly disturbed Earth's upper atmosphere from 50,000 light-years away, showcasing the staggering reach of these cosmic powerhouses. The magnetic environment around a magnetar is so intense that it alters the very vacuum of space, making it behave like a crystal that splits light into polarized beams. As photons pass through this magnetized emptiness, they twist and align, providing astronomers with direct evidence of magnetic fields far beyond anything we can produce on Earth. But these exotic remnants are only the opening act in nature's catalog of extreme phenomena. Across the universe may stretch invisible cosmic threads, capable of slicing through planets as effortlessly as wire through soft clay. These hypothetical objects, known as cosmic superstrings, are thinner than a proton, yet potentially longer than entire clusters of galaxies. They may be ancient scars left over from the infancy of the universe, formed in the first instance after the Big Bang, when the fabric of space-time itself underwent violent transitions. According to string theory, these cosmic strings mark boundaries where different regions of space cooled and crystallized in slightly different ways, like cracks spreading across a frozen lake. A single strand only a meter long would weigh as much as Earth, yet it would be so impossibly thin that it would have no meaningful width or height, only length. These objects exist on the boundary between matter and energy, between physical reality and the mathematical depths from which the universe emerged. The energy locked inside a cosmic string defies comprehension. A string extending from Earth to the Moon would contain enough mass energy to power human civilization for trillions of years, and all of it compressed into a thread with effectively no thickness. If such strings move through space, they would send ripples through space-time itself, gravitational waves that our most sensitive detectors might one day observe. Their signatures would be unlike those from colliding black holes or merging neutron stars. Should two strings cross paths, they could form loops that vibrate like gigantic cosmic instrument strings. But rather than producing sound, these oscillations would distort the fabric of reality, sending waves outward at the speed of light. Over time, these loops would radiate energy, shrink, and eventually vanish in a final burst of gravitational ripples, erasing themselves from existence. Some researchers even speculate that cosmic strings could serve as shortcuts through space-time. If two distant points were connected by a string, traveling along it might allow one to reach the destination faster than light moving through normal space, making them the ultimate cosmic highways. Others suggest they may reveal the presence of hidden dimensions, extra layers of reality beyond the three we perceive. What we see as a one-dimensional thread may be just a tiny cross-section of a much larger structure existing in higher dimensional space. These theoretical giants remain buried deep within the mathematics of modern physics, waiting for a generation of astronomers to confirm or eliminate them through future discoveries. 4 billion light-years from Earth, a black hole as large as our entire solar system unleashes a beam of particles that spans an entire galaxy. This jet, made of superheated plasma, races outward at 99.9% the speed of light. It carries enough energy to power 1 trillion stars, yet remains focused with surgical precision across distances that defy human imagination. Radio telescopes often detect them as razor-thin lines, even when they originate billions of light-years away. The particles inside these jets possess energies millions of times greater than anything produced by human-made particle accelerators. Individual protons hurtle forward at such extreme speeds that their relativistic mass increases thousands of times, transforming them into cosmic bullets of unimaginable force. When one of these jets happens to point directly at Earth, it appears as a blazar. Its brightness flickers and flares as the jet sweeps past us like a cosmic lighthouse. Turbulence inside the jet produces bright knots of material that seem to move faster than light, even though this apparent superluminal motion is merely an optical illusion caused by geometry and near light speed travel. This illusion highlights how close these particles come to reaching nature's ultimate speed limit. The most powerful quasar jets carry enough energy to heat entire galaxy clusters, carving enormous cavities in the surrounding gas, bubbles that endure for hundreds of millions of years. These cosmic blowtorches can halt star formation across regions millions of light-years wide, essentially sterilizing large portions of space. New observations reveal jets stretching far beyond the boundaries of their host galaxies, extending deep into intergalactic space where they continue to propagate for millions of years. These ancient structures preserve the signatures of black hole activity from a time when the universe was younger, more turbulent, and far more violent. Meanwhile, in a binary star system 30 million light-years from Earth, a white dwarf quietly harvests material from its companion star like a cosmic vampire draining stellar lifeblood. Over millions of years, streams of hydrogen flow onto the white dwarf's surface, accumulating gradually, like snow piling up on a mountainside. But this stellar snowpack is inching toward a deadly threshold, one that will trigger one of the universe's most precise and catastrophic explosions. White dwarfs are the compact remnants left behind when sun-like stars exhaust their nuclear fuel and shed their outer layers. These dense stellar cores pack the mass of our sun into a sphere no larger than Earth. A single teaspoon of their matter would weigh as much as a car. Their blistering surfaces glow at tens of thousands of degrees, hot enough to vaporize nearly any substance known to man. As a white dwarf siphons material from a companion star, the stolen hydrogen accumulates on its surface. Gravity compresses this layer into an ultra-thin shell, steadily increasing its temperature and pressure. The star becomes a cosmic pressure cooker, slowly heating this borrowed fuel until fusion begins to simmer at the surface. Once the white dwarf reaches precisely 1.4 times the mass of our own sun, what astronomers call the Chandrasekhar limit, its internal support fails. This limit represents the maximum mass that electron degeneracy pressure can resist. Exceeding it spells catastrophe. The star can no longer hold itself together. In an instant, the hydrogen layer ignites in a runaway thermonuclear inferno. The explosion tears through the white dwarf like a flame ripping through cosmic gunpowder, fusing carbon and oxygen into heavier elements like iron and nickel. The star obliterates itself completely. This event is known as a Type 1a supernova, one of the universe's most reliable yet destructive explosions. Every Type 1a supernova releases nearly identical amounts of energy because each one occurs at the same critical mass and undergoes the same nuclear process. Their consistency makes them invaluable cosmic yardsticks for measuring distances across billions of light years. For a brief time, the explosion shines with the brilliance of 5 billion suns. A single white dwarf can outshine an entire galaxy filled with hundreds of billions of stars. Its brightness rises quickly, then fades over months as radioactive elements created in the blast decay. These explosions manufacture and disperse essential elements across the galaxy. The calcium in our bones, the iron in our blood, and the nickel in everyday objects were forged in such titanic events. We are quite literally made of the ashes of ancient exploding stars. The shock wave races outward at thousands of miles per second, heating surrounding gas to millions of degrees. This blast can spark new rounds of star formation, enriching future solar systems with the heavy elements necessary for planets and for life. Far across the cosmos, 2 neutron stars, objects the size of a city yet more massive than the sun, spiral towards one another in a deadly gravitational embrace that has lasted millions of years.
These remnants of collapsed giants represent the densest form of matter that can exist without collapsing into a black hole. A single teaspoon from their surface would weigh 6 billion tons on Earth. As they draw nearer, their immense gravity distorts each star's shape, stretching and compressing them like cosmic taffy. The friction generates heat, raising surface temperatures to millions of degrees. Their orbit tightens as they lose energy through gravitational waves, ripples in space-time that carry energy away at the speed of light. By the final moments, the neutron stars whirl around each other hundreds of times per second, faster than anything mechanical ever created. Earth-based detectors can detect these waves, even though they alter distances by less than 1/10,000th of a proton's width. In the final seconds, the stars radiate away energy equivalent to 3 suns, causing their inward spiral to accelerate dramatically. When they finally collide, a burst of gamma rays erupts, followed by a longer-lasting explosion known as a kilonova. This cataclysmic merger literally shakes the universe, sending gravitational echoes across billions of light years. Within this violent crucible, elements heavier than iron are forged through rapid neutron capture. Atomic nuclei are flooded with neutrons so quickly they transform into unstable isotopes. These decay into stable heavy elements: gold, platinum, uranium, and many others. A single neutron star merger can create more gold than several Earths combined, flinging this treasure into space at 1/3 of light speed. Over eons, this material seeds interstellar clouds, eventually becoming part of new planets and asteroids. The explosion ejects debris moving at different speeds. The fastest material powers the initial gamma ray burst. Slower layers form expanding shells that shine for weeks as radioactive decay releases energy. The resulting kilonova glows with the combined brilliance of hundreds of millions of suns. 13.8 billion years ago, everything we know was compressed into a point smaller than a proton. All matter and energy, from the tiniest particles to the largest galaxy clusters, existed within a dimensionless speck. This was the Big Bang singularity, the ultimate expression of cosmic power, the moment the universe burst into existence. At this primordial moment, the familiar laws of physics collapse. Temperature and density reach infinity. Space and time have no meaning. The 4 fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were fused into a single unimaginable superforce.
Within the first fraction of a second, so brief that light itself could not cross a proton, the universe expanded faster than light. This phase, known as cosmic inflation, stretched space by unimaginable factors in an instant. The universe didn't expand into empty space, it created new space as it grew. Temperatures were so extreme that even the fundamental forces could not remain distinct. Only as the universe cooled did this unified superforce fracture. Gravity separated first, then the strong force, and finally electromagnetism split from the weak force. During the first minute after the Big Bang, the temperature dropped enough for atomic nuclei to form through a process known as Big Bang nucleosynthesis. Protons and neutrons, freshly assembled from cooling quarks, fused to create the hydrogen and helium that still dominate the universe today. Energy densities were so high that matter and antimatter annihilated each other constantly, producing bursts of pure radiation. For 300,000 years, the universe remained opaque to light. Free electrons scattered photons endlessly, preventing light from traveling freely. The early cosmos was a glowing, impenetrable fog, a universe filled with light that could not escape. Then came the era known as cosmic dawn. Electrons and atomic nuclei finally joined together to form the first neutral atoms, allowing light to travel unobstructed for the very first time. As the universe became transparent, this newly liberated radiation spread outward, leaving behind a faint afterglow we still observe today as the cosmic microwave background, a whisper from creation itself that fills the entire sky. But hidden within the quantum fabric of reality lies a possibility so unsettling that it could erase everything we know in the blink of an eye. The Higgs field, the invisible field that gives particles their mass, may not be in its lowest possible energy state. If it suddenly dropped into its true minimum, it would trigger the formation of a bubble of altered reality expanding outward at the speed of light, rewriting the laws of physics and obliterating everything in its path. This Higgs field permeates all of space, even the empty regions between atoms. Yet, like a ball perched on the top of a hill, it may currently rest in what physicists call a false vacuum state, appearing stable but only temporarily balanced. A shift to the true vacuum would fundamentally transform the nature of existence itself. If such a transition began anywhere in the cosmos, a sphere of true vacuum would erupt outward at exactly the speed of light. Nothing could outrun it because no form of matter or information can move faster than light. We would never see it coming. Life would continue as normal until the instant it arrived. Inside that expanding bubble, the basic constants of nature would change. Particles might acquire different masses or cease to exist at all. Atoms would be unable to form. The strong nuclear force could weaken, causing atomic nuclei to disintegrate instantaneously. Chemistry, biology, and every structure in the universe would vanish. The energy released during this transition would dwarf anything imaginable. It could exceed the total rest mass energy of all matter in the universe, unleashing more raw power than all stars and galaxies combined. Modern calculations suggest our vacuum may indeed be metastable, balanced precariously on the edge, waiting for the slightest disruption. High-energy cosmic rays, or even the final stages of black hole evaporation, could, in theory, trigger such a collapse. The frightening part is that quantum mechanics allows even empty space to spontaneously create a bubble of true vacuum. If the false vacuum state exists, the decay is not just possible, it is inevitable. Quantum mechanics guarantees that metastable states eventually transition to more stable ones, even if the probability is tiny. Given enough cosmic time, even the rarest events become certain. Vacuum decay would serve as the ultimate reset button for the universe. Everything, every star, every planet, every living being would be wiped away and replaced by a universe governed by entirely different rules. Nothing of our current world would remain, not even the memory that it once existed.
Some theories even suggest that vacuum decay might have occurred before, creating multiple regions of the cosmos with different physical laws. Our universe may be just one bubble among countless others, surrounded by domains where reality behaves in ways completely alien to us. In the earliest moments after the Big Bang, when the universe was smaller than a single atom and denser than a neutron star's core. Tiny fluctuations in density could have collapsed under their own gravity. These collapses might have produced primordial black holes, objects heavier than mountains yet smaller than atoms. These primordial black holes would wield gravitational forces so extreme that they distort space and time on scales far too small for the human eye to detect. Unlike black holes born from collapsing stars, primordial black holes could have formed with virtually any mass. Some might be as lightweight as a paperclip, while others could rival or even exceed the mass of our sun. The tiniest among them would exist at the crossroads of physics, where quantum mechanics and general relativity collide in ways we are only beginning to imagine. A primordial black hole with the mass of a mountain could be smaller than a proton, yet capable of generating a gravitational field millions of times stronger than anything achievable in Earth-based laboratories. In their immediate vicinity, space and time would twist into bizarre configurations, erasing familiar notions of distance, motion, and duration. Despite their microscopic size, these entities would be some of the most violent objects in existence. According to Stephen Hawking's groundbreaking predictions, black holes emit radiation and gradually evaporate. The smaller the black hole, the faster this evaporation occurs, and the more explosive its final moments become. A primordial black hole with the mass of a large asteroid would end its life in a cataclysmic detonation, releasing the energy of millions of hydrogen bonds. As these tiny black holes shrink to subatomic scales, their evaporation accelerates exponentially. In their final second, they could unleash more energy than the sun emits in an entire year, concentrated into a point smaller than an atomic nucleus. If large populations of primordial black holes exist, they may hold the key to one of cosmology's greatest puzzles, the true identity of dark matter. These invisible objects would exert gravitational influence without emitting a single photon, perfectly matching the mysterious behavior attributed to dark matter across the universe. Because of this, scientists have searched for signs of primordial black holes in some of the cosmos's most extreme environments. If a primordial black hole passed through a star, its gravitational pull would heat the stellar material, producing observable fluctuations in brightness. Collisions with neutron stars might generate detectable gravitational waves. Over billions of years, some primordial black holes could have grown by consuming matter or merging with each other. Today, they might be roaming the voids between stars, unseen predators waiting to encounter any stray matter that crosses their path. Their gravitational lensing effects might occasionally distort or magnify the light of distant stars, offering rare glimpses of their presence. The most massive primordial black holes may have acted as the seeds from which supermassive black holes eventually formed. This idea could explain how enormous central galactic black holes appeared so early in cosmic history, long before normal stellar evolution could have produced black holes of such size. Before the universe was even 1 second old, space itself underwent the most rapid and violent expansion in the history of existence. In a time span shorter than the time it takes a photon to cross a single proton, the universe ballooned from smaller than an atom to larger than a grapefruit. This astonishing transformation, known as cosmic inflation, marks the most explosive burst of expansion the cosmos has ever experienced. During this phase, space itself stretched faster than light, laying the foundation for everything that would eventually form. In just 10 cubed minus 35 seconds, the universe expanded by a factor of at least 10 cubed 26. To grasp this unimaginable scale, picture a lone atom suddenly swelling to a size larger than our entire solar system, faster than light could traverse its original width. Inflation was so rapid and extreme that it shatters any intuitive sense of speed or scale. At the heart of this phenomenon was a quantum field called the inflaton. This field permeated all of space, filled with colossal energy density.
Unlike ordinary matter, the inflaton generated even more energy as space expanded, acting as an inexhaustible cosmic engine. The larger the universe grew, the more fuel inflation had to accelerate it further. Inflation solved some of cosmology's most perplexing mysteries. It smoothed away exotic particles and topological defects that should otherwise still exist. It explained why regions of the universe that were never in contact nonetheless share the same temperature today. And the tiny quantum ripples in the inflaton field were stretched out across space, becoming the seeds from which galaxies, clusters, and cosmic structure would form billions of years later. The energy involved in inflation was beyond anything imaginable, greater than the total energy output of all stars across the universe over 13.8 billion years. When inflation finally ended, the inflaton field decayed violently into ordinary matter and radiation, reheating the universe to mind-bending temperatures and igniting the next chapter of cosmic evolution.
Some theories propose that inflation never truly ended, that it continues in distant regions of spacetime, spawning an endless multiverse where countless pocket universes expand independently, each governed by its own physical laws. Deep within the core of a rapidly rotating dying star, spinning more than 1,000 times every second, magnetic fields 1 trillion times stronger than Earth's magnetic shield twist matter into impossible shapes. This extreme environment gives birth to a magneto-rotational supernova, an explosion so powerful it can rival or even surpass the energy of gamma-ray bursts. As the star's core collapses, its tangled magnetic field lines stretch, twist, and snap, unleashing bursts of energy capable of powering our sun for billions of years. These titanic events hurl jets of magnetized plasma outward at nearly the speed of light. Atoms deform, molecular bonds disintegrate, and even the vacuum itself becomes birefringent, splitting light like a crystal under the strain of the magnetic fury. Magneto-rotational supernova forge exotic isotopes and unleash energies far greater than those produced in ordinary stellar explosions. Surrounding every galaxy, including our own, is a vast halo of dark matter, an invisible substance 5 times more abundant than the matter that forms stars, planets, and life. If dark matter particles can annihilate with their antiparticles, the energy released would be extraordinarily pure, far more efficient than any known reaction in the visible universe. In the densest hearts of galaxies, such annihilations could potentially outshine every star combined. Massive dark matter particles might produce photon pairs with energies millions of times higher than visible light. In the most extreme environments, cascades of these annihilations could sterilize entire regions of space. Cosmic rays offer yet another glimpse into the universe's hidden power. Some of these particles reach energies of 10 to the 20th electron volts, far beyond the capabilities of any human-made particle accelerator. A single proton at this energy carries the punch of a thrown baseball, compressed into the volume of an atomic nucleus. When these ultra-high energy particles slam into Earth's atmosphere, they trigger enormous particle showers that spread across thousands of square miles. While supernova can accelerate cosmic rays to high energies, only active galactic nuclei, powered by black hole jets stretching millions of light years, can boost particles to the absolute extremes. Their immense magnetic fields whip particles to near light speeds, producing streams of synchrotron radiation that light up the sky. Between atoms lies the quantum vacuum, a restless sea of zero-point energy where virtual particles flicker in and out of existence. Theoretically, this vacuum energy should be 10 to the 120th times greater than what we observe, one of the greatest unresolved mysteries in physics. Yet these ghost-like virtual particles produce very real phenomena. The Casimir force, Hawking radiation, and even the primordial fluctuations that seeded galaxies. Some theories suggest that the entire universe might have sprung from a quantum fluctuation in this vacuum energy. Beyond what we can see, there may be infinitely many other universes. Eternal inflation predicts an endless cosmic archipelago.
an infinite multiverse where every possible set of physical laws exists somewhere. Some universes collapse shortly after forming, others expand eternally. Some may even oscillate in endless cycles of birth and rebirth. Quantum mechanics offers another possibility. Every possible outcome of every event may unfold in parallel realities. By this logic, we inhabit a universe that appears fine-tuned for life simply because only such universes can produce observers capable of noticing its properties. If contact between universes were ever possible, it could unlock boundless knowledge, energy, and perspectives beyond imagination. It's even possible that the multiverse undergoes transitions between different vacuum states, reshaping the very nature of reality itself. And so, as we reach the end of our journey, we have witnessed forces spanning the smallest quantum scales to the grandest cosmic structures. The universe is not merely a container of power, it is power incarnate. Every atom in your body is held together by forces more intense than anything humans can create. Every star burns through nuclear fire. Every galaxy drifts through tides sculpted by gravity and dark energy. Yet the universe's greatest wonder may be its ability to produce complexity, beauty, and consciousness. We are made of stardust, born from supernova and neutron star collisions. We are the universe awakening to its own existence. Perhaps the most profound force in the cosmos is its capacity to understand itself through beings like us.